Hi guys, this video is about the revolution counter I've just built. It is kind of a side project because I'm currently also working on a wind turbine, and for that wind turbine I need to find out what RPM of the rotator corresponds to a certain power output. I thought I would share this information with you because revolution counters are used in many applications, and so here we go. Here are the parts I'm going to use to make a revolution counter. As a microcontroller I use an Arduino Nano clone, then a fork light barrier, which is a Sharp GP1S51. Then for powering the whole setup I use a lithium-ion battery, which is already equipped with a charger, the USB charger, and a step-up converter, which will convert the voltage of the battery to around 9 volts. And this step-up converter can also be switched on and off. So when charging it's switched off, and when using it's switched on, like this. Right, now let's turn it off again. And a TFT display, an IPS 240x240, which will later on display the RPMs. So here's the finished revolution counter. It took me a whole day of soldering, of programming and debugging, and now it finally works. It's equipped with everything for mobile use. There is a lithium-ion battery, which can be charged by the lithium-ion battery charger via USB. Here's the Arduino Nano board, and then it has a switch by which it can be turned on and off, and of course the main part, this fork light barrier, where you can see on the right a symbol which indicates the infrared LED, and on the left, on the side, we have the photoelectric sensor. There are 3 cables going to the fork, and indicating that it's a 3-pin fork light barrier. And the orange one is the signal cable. Those two are plus and minus. And there are 2 resistors going to the fork light barrier. One is going to the LED, it's a 150 ohm resistor, and the other one goes to the photoelectric sensor, it's a 1 kilo ohm resistor. And with this 1 kilo ohm resistor, when there is no obstacle inside the fork, the current that flows through the photoelectric sensor is around 3.68 milliamps, and if there's an obstacle, there only flows a current of around 1% of that, and so that's a big difference that can be measured. And then there's another resistor which is put between the load resistor, that is the 1 kilo ohm resistor, and the photoelectric sensor, which goes to the A1 pin of the Arduino Nano, to the analog pin. And that resistor has a value of 680 kilo ohms. Could be chosen way less than that. I accidentally chose such a big resistor, but it works, so I left it in there. And this resistor is really necessary, so the current does also go through the fork light barrier and not all through the cable to the Arduino Nano. So if there were no resistor in the signal cable, from the signal cable to the Nano, it would measure always the same current and the biggest value, so it would be useless. So this resistor is really necessary. You can see that later on in the video in the circuit diagram as well. So it's very compact. Perhaps it's the most compact revolution counter you'll ever see. I don't know. It's not very much bigger than the battery itself. And now let's turn on the switch. You can see that the TFT display is a little bit defective. Unfortunately, it was the last one that I had, but you can still see the numbers. Here you can see the circuit diagram. On the left we have the Arduino Nano, on top the TFT display with its terminals ground, VCC, SCK, SDA, RES and DC. On the right there's the fork light barrier, which is a 3-pin Sharp GP1S51, and there are 2 resistors going to this fork light barrier. On top the load resistor, a 1 kilo ohm resistor, which goes to the photoelectric sensor, and on the bottom a 150 ohm resistor, which goes to the infrared LED. And this resistor brings about 20 to 30 milliamps to the LED. And a third resistor, which goes from between the load resistor and the photoelectric sensor to the analog pin of the board A1. And this resistor really needs to be a little bit bigger. In this case I had chosen a 680 kilo ohms. It may work also with values like 10 kilo ohms as well. And this resistor is really necessary because otherwise all the current would go along here and not across the photoelectric sensor, and so there wouldn't be any enough current for here for something to detect, and this value would be essentially always the same, and you would not be able to measure any difference if something goes through the fork light barrier or not. And the line between the photoelectric sensor and the LED is internal. That is, it's inside the fork light barrier, so it's just for you to notice that there's a connection, because it's a 3-pin. And in case of a 4-pin fork light barrier, you would also have to get this line connected to ground, like this line. So those are the connections, and the photoelectric sensor, in case there is no obstacle in between, will deliver around 3.7 milliamps. And this value is connected to this load resistor of 1 kilo ohm. So with other values of RL, you will have different outputs here. But the bigger the values, that is, if it's bigger than 1 kilo ohms, the smaller the current will be, and so there will be less voltage to measure here on A1, and therefore I've chosen this one. And if you go to smaller values, then the current will not increase very much anymore, so 1 kilo ohm is really I think the best choice in this case. But if there is an obstacle inside the fork light barrier, the current of the photoelectric sensor will drop significantly to around 1% of the original current, and this difference can easily be picked up by the analog pin of the Arduino. What the Arduino does is it measures the voltage across the load resistor here, and subtracts this voltage from 5 volts, so you get a voltage of the photoelectric sensor instead of the load resistor. And this is done by values between 0 and 1023, where 1023 corresponds 5 volts and 0 corresponds 0 volts. So this is what it looks like in practice. This is the value of the analog pin, which is currently at 278, which corresponds to a voltage of 1.36 volts on the photoelectric sensor of the fork light barrier when there is no obstacle inside. And if I put an obstacle inside slowly, the voltage will slowly increase the more I push it inside. As you can see, now I pull it out again, pull it back inside completely, and the voltage rises to almost 5 volts. At this point there's only a small current flowing through the photoelectric sensor, and the voltage across it is, as can be seen, around 5 volts. Now I pull it out again and the voltage drops again to around 1.38 volts. As you can see, this value has changed a little bit. I think it is due to the fact that the device warms up while running. To test the accuracy of the revolution counter, I've built this little setup here with a multifunctional tool, which is set to have a maximum revolutions per minute of 20,000. Okay, start. As you could see in the previous clip, the test of this revolution counter was quite successful, as the maximum RPM of the multifunctional tool of around 20,000 RPM was reached. The display showed about that value, so we can say with certainty that the revolution counter works up to such RPM, perhaps even higher RPM. I haven't tested that yet. I hope you liked the video. If you did, please give a like, feel free to comment, and I would be happy if you subscribe. Until next time, bye!